Be like one step ahead of you. Okay, so today we are going to be starting Unit 6. There are 9 units, so we still need to do 4 of them to get through the content material. The way I have my schedule ready to go for the whole semester, if you want to see that, if you want to look at it, I'll print it off for you. I don't think any of you use it, and that's fine. But I have it all ready. I think we will have 10 whole class periods of review to prepare for the AP test. There are 2 class days that I will not be here because I will be on vacation right before spring break. And so I will have other works for you to do while I'm gone. But then our test this year, it used to always be the 1st of May. It really isn't now until the 6th. So that gives us a few extra class days to work before the test, before the big old exam. So this is Unit 6. It is all about thermochemistry. A lot of today should be a pretty good review of a lot of science that you learned maybe in middle school even, and some stuff we learned last year. So this is like sort of the introduction to thermochemistry, and then I believe Unit 8 or 9 is applications of thermochem. I'm not exactly sure why AP has you do one and then like wait a couple of units to do the other, but here we are. Okay, so thermochemistry, well, we know what the word chemistry means, right? But what does the word thermo mean? Or what does it make you think of? Heat. Yep. Okay, so when we on like the very first day of chemistry last year, we learned that chemistry is the study of matter, its properties, the changes it undergoes, and the energy associated with those changes. The energy associated with those changes, most usually in chemical reactions, is heat. There are, as we know, other forms of energy. There's electrical energy, and we spent some time talking about chemical processes like redox reactions that involve electricity. The other forms of energy are like the energy of, well, let's see. There are the 2 main forms, so let's break them each down. Kinetic energy is the energy of, what did Mr. B teach you in like 7th grade? I know, really go back into the recesses of your mind. Kinetic energy is the energy of motion. So if something is moving, it has kinetic energy. So the way this is expressed in chemistry is mostly the thermal energy of molecules or atoms or ions. A good thing to remember though is that thermal energy is the scientific way that we define heat. So when we get through this a little bit more, we'll remember that heat and temperature and thermal energy, it's complicated. Their relationship is complicated. But in the English language, we use all 3 of them like interchangeably. But in science, they're not the same things. Okay, so the other forms of kinetic energy would be mechanical energy, electrical, because remember that electrical energy is the flow of electrons, and so if electrons are flowing, that means by definition that they are moving. So that must be a kinetic energy form. And then another form of energy that we don't often think about is sound. Sound is, remember, actually a wave. And so therefore, because a wave has particles that, or it moves the particles, it is particles that are moving, or it moves particles that are in the medium that it's traveling through, that motion indicates that it's a kinetic form of energy. The only time, and I'm going to put this right back up here, the only time matter has zero kinetic energy. So the only time when matter is absolutely not moving is the theoretical construct we call absolute zero. Absolute zero is defined as 0 kelvins. It is a theoretical construct because it's not something that we are able to accomplish via experimentation. So scientists think that, well, if you could stop the movement of molecules, if you could completely stop all of their vibration, it would be at a temperature that would be 0, because you're saying that my molecules have 0 energy. Some people think that this, when you stop motion, you can also stop time. And if you could stop time, then you could time travel. So like, it's kind of like this like crazy, like philosophical, scientific thought process that's like a little bit nonsensical because it's all theory. The other form of energy that's not kinetic energy is potential energy. And potential energy describes like really what its name is. It has the potential to do something. So we really say that this is the energy of position, because where two particles are in relation to each other determines how much energy they have. For example, let's say that you're a student at the top of a building. We had this as a problem in AP Physics yesterday. A student falls from a certain distance and lands on the ground. Well, you have a greater potential to have broken bones if you fall from a higher height than if you fell, and my man is all crazy. If you fell from a lower height. So maybe then your bones wouldn't be all squiggly. In that problem that we did in AP Physics, we determined that the person fell 6.6 meters, which is like just around 20 feet, which seems like that might be something broken-y. So the higher you are away from something, like gravitationally, the more potential energy you would have. So I'm just going to then like reiterate that this is gravitational energy. And then there's chemical energy, which is also a potential energy. This is the energy that's stored in bonds. The best example of this is the energy that's stored in the bonds of fuel. So, how many of you guys have like cars that take the E85 gas? Do you know what that is? So there's like, when you go to most gas station pumps, there'll be like 3 options of gas. There is, usually the one in the middle is the cheapest. And then the one usually on the left is cheaper, but it's like, this one, okay, so this one like right now is like, let's say it's $2.79, and let's say this is $2.83. So they're like there's a little bit of difference, but really if you've got a 20-gallon tank and you're saving 4 cents a gallon, you saved 80 cents. Good for you. And then this one is, we're just going to write like major money signs, because this one is probably right now at like $3.79. So the difference, like why is there a price difference? Well, two reasons. This one used to always be quite a lot cheaper than the first grade of gas, but now it's not anymore. This one has the most ethanol, and the reason it is cheaper is because it has less energy stored in its bonds, and so it takes you less far. The reason that the 3 money sign last option of gas is usually the one that has no ethanol added. And so if you ever have to go and get gas for your lawnmower or your snowblower, you always want to choose this one because ethanol is bad for your small engines. When it burns, it produces water, and that really builds up in the smaller engine. Heaven, when you ride your motorcycle, do you have a preference of gas that you fill up with?
We always get premium.
You always get premium because that's a smaller engine, and you don't want to, like, the engine of your motorcycle is like the thing of the motorcycle that like makes it, right? And so if you're going to like cheap out and use that middle section of gas, the potential for like hurting your engine is greater because it produces that water, and that's kind of like what gives you that like knocking sound in your engine. The more modern engines are able to accomplish like dealing with that waste water that's produced when ethanol is consumed. And so that's why, like, if you drive an older car though, it like you won't be able to use the E85 gas. So this is really what we call the E85. This is like really would be E90 because it's still 90% gas. There's like up to 10% ethanol added. Sometimes you can even find the E88. It's not that much cheaper. You've saved 80 cents if you've got a 20-gallon tank, which is a pretty big gas tank. I would say don't ever buy this. Like, it's not worth the 80 cents. You could probably find that like in your, like underneath your floor mat. Okay, so that is the chemical energy that's stored in bonds. We'll talk a little bit later on in class about why there's more energy stored in this kind of gas than in this one. But for right now, just know that energy gets stored in those bonds, and when they're broken, that's what gives us the fuel. And then, the last one is electrostatic energy. Electrostatic energy is the energy that is associated with two things of different charge being next to each other. So just like two ends of a magnet, when they get close enough, they will like come together, I guess, and they'll kind of do it like vigorously, I guess, depending on how powerful your magnet is. Same thing that happens with ions, especially in solution. When they're next to each other and they see each other, they just are attracted to each other. Okay, so this should be a lot of review. This maybe is not. Oh, we might have done this last year. Did we talk about the first law of thermodynamics? You maybe don't remember what it is. That's okay. You probably have heard it though. The first law of thermodynamics states that energy is the conserved quantity. So in English, what does that mean? Energy cannot be created or destroyed. This is again a theoretical construct. So the universe is what we say, like the entire energy of the universe cannot be created or destroyed. That amount of energy has to stay the same. But we also know that the universe is expanding. And so how is it possible that the universe is expanding if energy is remaining constant? So because we know that the universe, from our understanding, the universe is currently almost 154 billion light years across. So in order to travel from one end of the universe to the other, it would take you 154 billion light years. That's almost like too much for us to even compute in our minds. And so how do you know how much energy is in this vast, vast space that you can't even like wrap your head mentally around? This is a theoretical construct. All right, so that being said, we know that energy isn't always like perfectly conserved. For example, Matthew, do you have in your water bottle right now, do you have a hot drink or a cold drink?
Probably cold.
It's probably cold. Was it, did it start hot?
No.
Okay, so it was cold. Anybody drinking coffee today? Okay, well, let's use Mr. Dermis as an example because that man drinks like 100 ounces of coffee in a day. Okay, so we know that if energy were to be completely conserved in a thermos, what would happen is that when you poured your hot coffee in at the beginning of the day, it would stay that exact temperature for as long as it remained in the thermos. But we know that that's not a true thing because eventually, like, your ice will melt in your water bottle. Eventually, your coffee will become room temperature. And that's because the system that we're talking about is losing energy to the surroundings. So before we go any further, I just want to define these words again. You can make a lot of different comments about energy being conserved by how you define your system and its surroundings. So if you say that the entire universe is your surroundings, energy has to be conserved. If you say that the system and the surroundings is your thermos or your like place where you're keeping the things cold, then you have to account for the fact that energy will be lost because this is not going to be able to hold in all of that heat or prevent heat from coming in if it's cold for all of time. So defining your system and your surroundings becomes a critical thing. A little bit less so for us in chemistry than it is in physics, because for us in chemistry, we can look at chemical reactions and call that the system. Whereas in physics, we kind of have to think like, yes, it's like nice for us to think that ignore friction and air resistance. But we know in the real world, friction and air resistance are a thing because otherwise we wouldn't be sitting in our seats, we'd be floating in the air. Okay, so let's talk then a little bit about temperature versus heat. Okay, so the first thing is that heat and thermal energy are the same thing. Heat and temperature are not. The more, and I'm going to use the term thermal energy because heat has a previous, we have a previous relationship with that word, and I don't want us to confuse it with its scientific definition. The more thermal energy a substance has means that the more kinetic energy each particle of the substance has. So the greater the heat of your substance, the more thermal energy it has, the faster your molecules are moving. I use particles here because it could be molecules, it could be atoms, it could be ions. So then though, the total thermal energy of a substance is, and now because I don't want to write all these words down, I'm going to use the Greek letter sigma. Do we know what that word means? What this means? This is sum of. What's not funny here?
Sigma.
So the total thermal energy of a substance is the sum of all of its particles' thermal energy. So then what is the difference? What does the temperature have to do with this? I'm just going to, I know I'm in your way, I'm sorry. I don't think that works. Oh, look at this. I'm learning. Okay. So then temperature is really the average thermal energy of the substance. So temperature and thermal energy is kind of like the chicken or the egg. Which one comes first? Well, I just saw a new report in my American Chemical Society journal that says that there's a protein in eggshells that can only be made by the hen, by the chicken, when it is in her body. And biology is not my thing, so I'm not speaking to the process of the hen giving birth to the egg. I don't know anything about that. But so they postulate then therefore that the hen must have come first, the chicken must have come first, because if the protein in the eggshell can only be made by the chicken must have come first. But where did the chicken come from? I don't know. Just passing on that little tidbit of scientific evidence there. So then therefore, the total thermal energy thermal depends on the amount of the substance and what the substance is. Or in other words, its identity. So this would be my final point. Those 3 dots like that in the shape of a triangle stand for the word therefore. Okay, any questions about that? This is all pretty still theoretical. Not any mathing, not any figuring out yet. Let's talk a little bit about heat transfer. Heat transfer always occurs in one way. Heat is always transferred from hot to cold. So let's talk about 2 different situations here. Let's say that this is my thermos and I'm going to start with my coffee, and so it's going to be hot. Because my thermos is not a perfect insulator, my heat is going to transfer someplace. So because it always is going to go from hot to cold, what's going to happen is that the thermal energy of your coffee is going to leave your thermos and warm the surroundings. How will you feel this? You will feel this as it being hot because you are the surroundings, not the system. You are not the coffee. Versus, let's say in the same thermos, sometimes you use ice water. I personally, like, I have many different water bottles. I like to buy a new water bottle all the time. My poor husband. But I like, they all have their own like designation. So if I drink coffee out of one of them, that's like the coffee cup then for always. Or if that's the one I use for my hydration multiplier, that's the one that always is used for that, because I feel like cross-contamination is a thing. And I don't want my water to taste like really thin coffee. You know what I mean? I'm weird. Maybe you guys aren't. Okay, so let's say you've got lots of the ices in here. And that's very nice because heat always has to travel from hot to cold. You will feel this differently, but it's going to happen in a way that's like not always obvious. Heat from the surroundings is going to come in and make those ice cubes melt. You will feel this as cold. Because where is that heat coming from? It has to come from someplace. If you're touching the container and it feels cold to you, the heat is coming from you. And the sensation that you're feeling is actually the heat leaving your body. That's why it feels cold to you. So when you go outside, today is actually a fairly colder day than it's really been, like this whole winter. So when it feels cold to you, what you're experiencing is the thermal energy of your body leaving you and really warming the environment. That's also why, like, if you're in a room, if you're like packed with a bunch of people in a room, or like at homecoming when it gets so hot, that experience is like people's bodies like losing their thermal energy to the cooler air surroundings. And then because it's coming off of everybody then starts to feel it because it's just raising the temperature of the entire place. And you're in a small surroundings. Okay, so then let's talk a little bit about the two different, like, so what we were just talking about. Let's describe our chemical processes using these words. So endo and exo are prefixes and they always mean the same thing. Exo means outer. So like if you're talking about the exoskeleton, that would be something that's on the outside of a creature's body. In an exothermic chemical process, what's happening is that heat is traveling from the in the system situation to out of system, aka surroundings. Okay, so what else, like other ways of describing this? Heat leaves the reaction. Another way to describe that, heat is produced. Another way to describe that, heat is actually a product in the chemical reaction. If that's the case, these tend to be spontaneous reactions. Now, the caveat here in AP Chemistry on these spontaneous reactions is that usually what in these processes that we're thinking of, it's spontaneous after ignition. So if this is your energy diagram of this reaction, and here is your reaction path, this, remember, is your activation energy. So once it's spontaneous because once the activation energy has been achieved, it's a downhill slope after that. You don't need to keep adding energy. So remember when we lit the sink on fire? The reaction kept going until all of the reactants were used up, but I had to ignite the sink first. I had to drop the match in. I don't have to keep lighting the match though in order for the reaction to progress, but I did have to start the ignition process. So in the same way that when you turn your car on, your spark plugs they do just that basically. They make the spark that ignites the reaction. And then after that, your spark plug doesn't really need to do anything unless you have the cars that have the auto stop, then they do. I think that is how, because it has to like refire I think that's how that works, but I'm not quite sure now that I'm thinking about that, I think I have to look into that. I'll check my facts on that. Yes, so that would be a spontaneous but after ignition reaction. Endothermic is pretty much exactly the opposite. So endo means inside. So we all have endoskeletons because our skeletons are inside our bodies. And except in the case of like in Home Alone 2 where you can see Marv's skeleton, you know, when he like touches the sink and he electrocutes, then you can see his endoskeleton, but he would be dead. So in the case of an endothermic reaction, heat from the out of system or the surroundings is added to the system. And so because everything is oppositely true, heat enters the reaction. I'm going to combine these two statements here into one. Heat here is a reactant. So in other words, heat is needed like continuously for every bond, we'll call it bond making. It could also be for bond breaking. For example, when you dissolve salt in water, that's an endothermic process. And so in order for the salt to really like dissolve more and more, you would have to heat it up somehow, like on the stove or in the microwave or whatever. You need to like constantly add the heat to make it dissolve. To us, exothermic reactions feel hot because we are the surroundings. For those of you who are in sports, or if you've ever like in gym class, I suppose, after you work out, sometimes you can feel like you can like feel that chill. You are the system, and so you're losing energy to your surroundings. What you're experiencing is your heat being lost because now you're the system. These reactions feel cold because, like I said before, when you're touching the thing, you're feeling the heat leave you. So like you can touch, most of you are next to something metallic right now. You can like touch anything metal and it'll feel cold to you. That's because it is taking your heat away. Metals are a very good conductor of heat. And so that's why they want to pull your heat away. And right now they're at the temperature that is the room, which is about 25 degrees Celsius. Your temperature in Celsius is 37 degrees. So remember, heat travels from hot to cold. 37, 25, you should feel that cold. You should feel that difference. All right, we're almost to the end here, friends. We're almost to the end. A couple of things. Hopefully at some point you learned the formula for kinetic energy. Kinetic energy is equal to 1/2 times a substance's mass times its velocity squared. And it has a unit of joules. Not the joules that you're not supposed to use in the bathroom. Joules as in like the scientist Joule Thomson. And so the unit is actually equal to kilograms times meters squared divided by seconds squared. Like, that's how you get a joule from this mathing of your units. Excuse me. So in order to use joules, you're going to always calculate mass in kilograms, which is not something we normally do in chemistry. Usually it's always grams. Velocity is calculated in meters per second.
Wait, what's the underlined part?
Mass times velocity. That maybe is too confusing. And then v is squared, velocity is squared.
And then you said mass in kilograms?
In kilograms, yep. Velocity in meters per second, but then when we square that, it becomes meters squared per second squared. The other formula is a reminder for you from last year. We spent quite a lot of time on this. The change in energy is equal to W plus Q, where W is work, which is measured in joules. Usually, but there's another unit, I'll show you that in a second. And then Q stands for heat. Why is it not H? We'll get to that. And remember that if you're going to add two numbers, they got to have the same unit. You can't be adding joules and kilojoules because that makes a nonsense number. And so then let's see, the last thing I think I wanted to tell you is that there's another unit of measuring energy, and that's the calorie. 1 calorie is equal to 4.184 joules. Hang on, let me make sure that that's true. Yes, that's true. This is lowercase calorie because the calorie on your food is actually capital C calorie, which is equal to 1 kilojoule, 1,000 joules. So I'm not going to worry about this for right now. I'm going to, in fact, erase it. But this calorie is not the same as the calories that we know of. Anybody got a bubbler today?
Bubbler?
Yeah, do you know how many calories are in a bubbler? I think it's 35.
I thought it was 15.
Oh, okay, 15, something like that. So 15 calories.
Either 15 or 5.
Oh, okay, so it's a small number.
Yeah.
But let's just say it's 15 for our purposes here. 15 calories for the bubbler would really be equal to, in science land, like our calories, 15000 calories. Why did they do that? Yes.
What's in parentheses under heat?
Oh, the joule.
So they're both joules?
Yeah,
Okay.
I mean, for us, we'll mostly use joules, but just remember, if for some reason you get a problem that is, here's one in calories and here's one in joules, you can't add different.
How do you switch from calories to joules?
Here is your unit
So
conversion.
that's 1 cal.
Yep, 1
Okay.
calorie is equal to 4.184 joules. Okay, I got the homework for you. All right,
Thank you.
so I tried to be quite a bit more deliberate about the homework questions that I asked you this time. So there aren't as many, but that means that, like, we don't have as many opportunities to practice those either. So just keep that in mind. Yes, it's a little bit less of work, but it probably means I won't do as many of them in class as well.
Almost
So
one.
you may do, you are able to do all of those book problems. These book problems are pretty simple. So if they're really complicating to you, like if in your mind you're like, I don't know how to do this, probably because you're overthinking, because they're pretty simple. And then the last ones, you actually know how to do because we learned calorimetry last year, but I will teach you that again on Monday. So you can, for me, work on those book problems, and I'm so confused. What time we get? Oh,
10:40.
40, 41, right? So you got like the next 25 minutes to spend working on Nancy Pelosi. Oh, anytime we got a picture of her, it's a great day. So you've got some time to work on that. And if you want me to check your work, I'm happy to do that.
And then, is it the same as it was the last year where it's like